Okay, section 3. Now we're going to get into the binomial distribution. Okay, some vocabulary that we need. A trial represents each repetition of an experiment. And the outcomes, those are all the different things that could happen for each trial. Now with a binomial distribution, we are interested in experiments that there are only two possible outcomes. And if you think about what the prefix bi means, it means two. So we are really only going to be focusing on experiments that have two possible outcomes. And our possible outcomes we're usually going to call success and fail. Now a Bernoulli trial is an even more special kind. There's three things that have to happen in order to have a Bernoulli trial. First thing, only two outcomes are there, success or failure. Second thing, the trials are independent, so one trial does not influence what happens next. And the third thing, the probability of success, which we use a p to represent, remains the same from trial to trial. We are going to be focusing mostly on Bernoulli trials. Okay, binomial coefficients. May not remember this from Algebra 2, but when I have a plus b, that quantity squared, it means I have a plus b times a plus b. Well, I've gone ahead and I've FOILed that out for you. And we get 1a squared plus 2ab plus 1. What I want you to pay attention to is notice that we have a 1, a 2, and a 1. So when I square something, my coefficients are going to be 1, 2, and 1. Now you hopefully recognize Pascal's triangle, maybe not though. What Pascal's triangle is, it's this arrangement of numbers. It'll always be this arrangement of numbers. And our row 0 starts with the number 1. Row 1 has 1 and 1. And now row 2 is 1, 2, 1. Now to get Pascal's triangle, we always start with a 1 in this first position here. And then to get this number, you take the sum of the two numbers above it. So 1 plus 1 gives me a 2. And then our ending is always a 1. So down here, to get this 10, we took the sum of the 4 and the 6. To get the 5 right here, we took the sum of the 4 and the 1. Now Pascal's triangle doesn't stop here. It keeps going. So it doesn't stop at row 5. It goes infinitely long. So our next row would be a 1, and then 1 plus 5 is 6. 5 plus 10 is 15. 10 and 10 is 20. 10 and 5 gives us another 15. And then a 6, and then a 1. So we could continue doing Pascal's triangle infinitely long. But one thing I want you to notice, look here at row 2. We see that 1, 2, 1 again. So when we square something, that puts us in row 2 of Pascal's triangle, and we can get those coefficients. You might be wondering what this has anything to do with stats, and that's because these are also called binomial coefficients. Now remember, we're talking about binomial distributions, so these binomial coefficients are going to play a huge role in a formula we'll have in just a little bit. Now our binomial coefficients are n choose x. Remember, this notation right here is just a fancy way of telling us we have a combination. So we're going to have n choose x, and that's our formula for our combinations. Now the way we can use Pascal's triangle for that is when we have 2 choose x. So we are in row 2, it's like we're squaring something. Our first number here, this 1, is 2 choose 0. Our second number is 2 choose 1. Our third number is 2 choose 2. Now you can imagine down here in row, there we go. In row 4, to get the 1, we would have 4 choose 0. To get the 4, you would have 4 choose 1. And if you don't believe me, you can try it on your calculator. But 4 combination 1 will give you a 4 back. To get the 6, we would have 4 choose 2. That would give us our 6. And then 4 choose 3 would give us this next 4. And 4 choose 4 would give us that 1. So there's this relationship between expanding some algebra binomials, Pascal's triangle, and binomial coefficients. You're not going to need to know that relationship, but just be aware of it, that it is there, because it might be able to help you out. Okay, if you read that one, we're talking about mortality rates of people who are 20 years old right now. They have an 80% chance of being alive at the age of 65. So part A says formulate the process of observing which people are alive at age 65 as a sequence of 3 Bernoulli trials. So basically what they're wanting you to do is go through that list we had for Bernoulli trials and explain what each one means. So number 1 from the Bernoulli trial list says only 2 outcomes, success and failure. Well, in this case, we do have 2 outcomes, either alive or dead. And just for this particular problem, let's denote a success as being alive and a failure being dead. Okay, the second thing on the Bernoulli trial list says the trials are independent of each other. Well, what you have to realize is if they are just randomly selecting people, it's not one person's death or living isn't going to influence the next person that they select. So they would be independent of each other. And then part 3 says the probability of success remains the same from trial to trial. So for this particular example, the probability of success is 0.8 for every single person. So it remains constant from trial to trial. Part B says obtain the possible outcomes of the 3 Bernoulli trials. Well, what they're wanting you to do is list them. So we're going to go ahead and start listing them. So we could have success, success, success. So all 3 people are living. We could have success, success, failure. So the first 2 people are living and the last one is dead. We could have success, failure, success. So the first one and the last one are living. Or we could have failure, success, success. We could also have failure, success, failure. We could have failure, failure, success. We could have failure, failure, failure. I'm missing one. We could have success, failure, failure. So those are going to be our 8 different outcomes that we could have. Now part C says determine the probability of each outcome in part B. So what you have to think about now is to get success, 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 I would have to have the first person live. So that's a 0.8 probability of living. Second person also has to live, so that's another 0.8. Third person also has to live, so that is a third 0.8. I could write that a little bit shorter and write it as 0.8 to the 3rd power. Okay, now in order to get success, success, failure, well, I'd have to have 0.8 for the first person because they lived, 0.8 for the second person because they lived, and now the failure. Well, if you have a 0.8 chance of living, that means you have a 0.2 chance of not living. So our failure is 0.2. Now I could rewrite that, if I wanted to, as 0.8 squared times the 0.2. The next one, success, failure, success. That would be a 0.8. My failure would be 0.2, and my success would be 0.8. So I could rewrite that one also as 0.8 squared times 0.2. So go ahead and finish out each one of these. Okay, I finished calculating those, and then I went ahead and actually multiplied it out, so the 0.8 times 0.8 times 0.8 is 0.512. So that would be part C, the probability of each outcome. Now part D says find the probability that exactly 2 of the 3 people will be alive. So what we need to do is we need to come over to our list and find out which ones have exactly 2 people alive. So we're looking for 2 successes. Well, as you can see, I have 3 different ways of getting those 2 successes. And if you look over here, notice that their chance of happening is exactly the same. They all have the same probability. So I can look at this 2 ways. I can look at it as 0.128 plus 0.128 plus 0.128, or I could write it a little bit shorter and say I have 3 times 0.128. Either way you do it, you're still going to get the same thing, which is 0.384. So there's a 0.384 chance that exactly 2 of the people will be alive. Okay, in part E, it says obtain the probability distribution of the number of people of the 3 who are alive at age 65. So now what they want us to do is they want us to do a probability distribution. So we need to make our table where we have lowercase x, which represents the number of people alive, and then the probability that capital X equals x. So my chance of 0 people being alive, well, I only have one way that 0 people are alive. So I would have 1 times that 0.008, which is going to be 0.008. Now, if I'm looking at one person being alive, well, in order for exactly one person to be alive, I've got these 3, I should have 3, okay, there's my third. Those 3 options right there. So I've only got 1 success in each of these cases. So I've got 3 at 0.032. When I multiply that out, I get 0.096. Okay, exactly 2 being alive, we did right up here, so that's the 3 times 0.128, and that's equal to 0.384. And then the probability of exactly 3 people being alive, well, I've only got one way to get all 3 of them alive. That was this very top choice here. So I have 1 times the 0.512, which gives me 0.512. So that would be my probability distribution. Now, one thing I want you to look at before we go on is look at these numbers right here. The 1, 3, 3, and 1. If we go back, notice how I have that in my Pascal's triangle, the 1, 3, 3, 1. So I could have came up with those numbers. It's in row 3. So to get the 1, I would have had 3 choose 0. To get the 3, I would have had 3 choose 1. To get the next 3, I would have had 3 choose 2. And I would have had 3 choose 3 to get the last one. So jump back to the slide ahead here. For this first one, it was 3 choose 0. Well, where does that 0 come from? That's our x value. The next one to get that first 3 was 3 choose 1. There's my 1. The second 3 was 3 choose 2. That's where I get my 2 from. And the last one was 3 choose 3. That's where I get my 3 from. So all of these had to do with 3cx. Well, now we have to decide, where did the 3 come from? Well, the 3 came from the fact that we had 3 trials. We had 3 people that we were testing, whether they were alive or dead. All of this pattern is summed up in the binomial probability formula. Okay, for our binomial probability formula, in n trials, so that would be like our 3 people we had, the number of outcomes that contain exactly x successes is equal to n choose x. So that was our 1, our 3, and our 1. So to get the 1, I had 3 choose 0 because I had n outcomes and I wanted exactly 0 successes. So then let x denote the total number of successes in n Bernoulli trials, with success probability being p. So for our example, this was 0.8. Then the probability distribution is this. So we've got this nice formula that will do our probability distribution without having to list all of our outcomes. Now, the formula really looks strange at first, but remember, this n over x is really combination. So if we did that, the probability that exactly 2 were alive from the last example, we would have done 3 choose 2 because I wanted exactly 2 to be alive. My probability of success was 0.8. Then I raised that to the x power. Well, the x power is how many I want to be alive. So I'm going to have 2 of them. And then this 1 minus p is actually my probability of failure. So that is 0.2. And then the n minus x, well, I had 3 to choose from, and I wanted 2, so that's going to be to the first power. Now what this means is we want exactly 2 to be alive, so we have success, success, failure. We have 2 successes, which is why it's squared, and we had 1 failure, which is why it's to the first power. And then this number right here tells us the number of ways that it could have happened. So we can get our distribution from our binomial probability formula.